Hello, this is Guillermo Campitelli, and in this video I'm going to talk about the concept of estimation in statistics that we use in psychological research. Okay, parameter estimation is what I'm going to talk about in this video, but parameter estimation is one of many inferential approaches in statistics. So inferential approaches are approaches in which we make an inference about something else. So we've got some data and we use those data to make an inference, not just about the data, but about something else. So parameter estimation is the approach that I'm going to talk about in this video, but there are other approaches that I will talk about in other videos: model comparison and hypothesis testing. Okay, so in previous videos I talked about probability a lot, and the idea is that in statistical inference we are going the other way around. So in probability theory we start with a distribution, and once the distribution is given, we determine how probable an event is. For example, if we know a distribution, a probability distribution, we use that distribution to determine how probable is to observe a value between 0.5 and 1. So that's probability theory, what allows us to do. Now, statistical inference, we use probability theory, but in a different way. What we have in statistics is the actual data, that is, the event that occurred. For example, we observed a value between 0.5 and 1. Now, once we observe this value, what we want to know is from which distribution this value comes from. Yeah, so we are using the tools of probability theory, but the direction of the process is the opposite. Okay, so in parameter estimation, we have a lot of concepts that I'm going to briefly explain here. Obviously, the most important is the concept of parameter. And parameter sometimes is a confusing term because we've got different conceptions of parameter. The most common, and the one that we use a lot in this series of videos, is that a parameter is a numerical characteristic of a population. So we got a population, we want to know a numerical characteristic of it. For example, the mean of a variable in that population, the standard deviation of a variable in that population, the proportion of people in that population who prefer one option over others. A group mean difference, so in that population we separate them into groups, and we want to know how they differ in one variable, the mean of those groups, how it differs. Or a difference score. For example, we got in the population people are requested to be measured twice. They are measured twice, and we obtain the difference between these two measurements. Or a correlation. So basically we've got the people in the population, we obtain a measure, and we obtain a second measure, and we want to know how correlated these two measures are in the population. Okay. Now, a parameter is also, we saw the concept of parameter in probability theory as a parameter of the distribution. Now, sometimes when we use we use distributions to illustrate or to represent a population. So in this sense, when we talk about the mean of a distribution, then it corresponds to the mean of a sample. So in that case, the parameter of the population and of the distribution are the same thing. But that's not always the case. So we need to take into account that there are these two concepts of parameter. One is a numerical characteristic of a population, and another one is a tool within a probability distribution. Okay, another concept in parameter estimation is a statistic. A statistic is a numerical characteristic, but not of the population, rather a numerical characteristic of the sample that we collected, that we extracted from that population. For example, the mean of a variable in the sample, the standard deviation of a variable in the sample, the proportion of participants, not of the people in the population, the participants in the sample who prefer an option. In the sample, we separate the sample in two groups, and we want to calculate the mean difference in a variable. Or the people in the sample are measured twice, and we obtain a different score. Or the correlation. We measure people in two different variables, and we want to know whether there is a correlation, and for that we use the correlation coefficient in the sample. Well, we've been talking about population and sample, we haven't defined that. So, and it's a bit tricky. The typical definition that you are going to find in methodological textbooks in psychology is that population is a big set of individuals. So typically, if we do human psychology, we are talking about people. So it is a big group of people, all humans, all children, all Australians. So it's a big set of individuals. Now, in statistics, probably if statisticians see what I'm saying here, they will kill me, but this is my interpretation of what population means in statistics. It is a big set of values instead of a big set of individuals. And sometimes population in statistics is a theoretical distribution. But I would like to think of a population as a big set of values. And you're going to see how these will be helpful when I explain the issue of sampling distributions in a while. Okay, so same thing regarding a sample. In psychology, we typically talk about sample as a small set of individuals who we extracted from a population of individuals. But in statistics, the sample is a small set of values extracted from a population. So we've got a big set of values, we obtain some values from that population. Okay. The concept of estimate is very important in parameter estimation. So an estimate is a value or interval of values that we use to estimate the value of a parameter. For example, we use the mean of a sample as the best estimate of the mean of the population. So the mean of a variable in the sample is the best estimate of the mean of the population. And for example, the correlation coefficient we use as an estimate of the correlation in the population. Okay, so in parameter estimation, there are many approaches, and I'm going to show you 3 of them. But it's important to say is that within each of these, there are many varieties of approaches. So what I'm going to show you is probably the most representative or the most popular within these approaches. So the frequentist approach, which is also, I'm going to call it the traditional approach, the Bayesian approach, and the resampling approach. In this video, I'm going to talk about the frequentist approach. Okay, so frequentist approach. So in this approach, there are a number of steps. The first step is to obtain a sample of participants that is representative of the population of interest. So if it is not representative, the sample, if we are interested in a population but we obtain a non-representative sample, we cannot make an estimation about parameters of that population. So this is important. We need to have a representative sample. Now, what is a representative sample? Well, a representative sample should be representative in the variables that we are going to measure, or that are related to the ones we are measuring. So, for example, if we know that gender doesn't affect the phenomenon we are investigating, so male and female perform at the same they have the same performance level. If we know already that gender is not an issue, so it doesn't affect the variable of interest, we don't need to have a proportion of male and female that is representative of the population. Now, if gender is related to the variables of interest, then we need to have the same proportion of male and female in the sample as in the population. So this is very important, because in psychology typically we don't obtain randomly samples from the population, and there is a debate whether the samples we use are representative or not. And in some instances, the samples we use are not representative, but if we take into account that a lot of things that we study in psychology are not influenced by a lot of variables that typically are important in other disciplines like economics or sociology, then the samples that we use are representative, even though they are not obtained randomly from the population. Okay. This is the first step: obtain a sample, measure in the variables that are important for the study, and that's common to all the approaches. Now, the second part is to obtain sample statistics. Then we need to make a point estimate of population parameters based on those sample statistics. When we have the point estimate, we use a sampling distribution that assumes that point estimate is true, and then we make an interval estimate of population parameters. Why we make an interval estimate? Because the point estimate we make, so we say, for example, my best estimate of the mean intelligence in the population is 104. Well, obviously the estimation cannot be perfect, so that 104 will have a degree of error. So we want to give it an interval of values rather than a point estimate, in which we are pretty sure that the population mean will be within those values. So that's the interval estimate. Okay, I'm going to explain this with an example, and it is important to establish that what I'm going to explain now is not what the researcher would do, because statisticians found shortcuts to what I'm going to explain. So basically, instead of doing what I'm explaining, they use shortcuts, and those shortcuts are implemented in statistical software. So basically, the psychological researcher never gets to do what I'm explaining now. But the idea of these videos is to understand what underlies the analysis we typically conduct. Okay, so let's say we want to know about, we want to estimate the proportion of people in a population who have anxiety. Okay, so let's say we've got a sample of 250 people, and they received the diagnosis of anxiety or not. So basically, in this sample, which is representative of the population, 200 were diagnosed with no anxiety, and 50 were diagnosed with anxiety. So this can be expressed in counts, so 50 out of 250 yes, and 200 out of 250 no's. It can be expressed as proportion, so 50 out of 250 is a proportion of 0.2 or 20% of the population having anxiety. So we want to estimate in the population what's the proportion, because and this is important. So far the examples I gave, the statistic and the parameter are the same, the mean of the sample, mean of the population. But in this case we can use the counts of the sample to determine the proportion in the population. And here we use 50 as the count, and in the population obviously we cannot count, because if the population is all humans, there are 7 billion people, so we are not going to come up with a count of the people who would have anxiety. So we come up with a proportion, right? Okay, and in this case, and I said 7 billion, but it's a very imprecise number, so the count would be very imprecise as well. So therefore we use proportions rather than the count. Okay, so we've got this sample, 250 people, and we've got 250 observations or values. 200 of those values are no, 50 are yes. Now, what we do is to we have to construct a sampling distribution of the statistic, and let's call it the statistic the yes count. So how many yeses we have in a sample. So in our sample there were 50 out of 250, or 20%, or 0.2, a proportion of 0.2. Now, in order to construct a sampling distribution, we have to assume that the population has a proportion of 0.2 of people with anxiety. Yes, so we've got a population of values with 200 of yes values and 20% of yes values and 80% of no values. So now from that population, let's say that we actually do it. We actually create a population with 20% of yes values and 80% of no values. Let's say we generate in a computer 1 million values, and 20 of those who are yes, and 20% are yes and 80% are no. So from that population of values, we obtain a sample of 250 values. So basically we are simulating what we actually did in our study. Now, in that sample of 250 values, we calculate the number of yes values in that sample. It typically is close to 50, but it's not going to be 50 all the time. So we record that value, and then we repeat this procedure 10,000 times. What I have to say is we do with replacement. So we put back those 250 values to the population of 1 million values, and we obtain randomly a sample of 250 values. We count how many of those are yes, and then we record that number. We return those values to the population of 1 million values. We obtain a random sample of 250. We count how many yeses, and we record that number. We repeat this procedure thousands of times, let's say 10,000 times. Now we've got 10,000 yes count values. Okay, so with these 10,000 values, we can use them as scores and generate a distribution. So we can generate a histogram. Okay, so we've got these 10,000 values, and we generate a histogram with those values, and we obtain a distribution like this one. So I actually did this with the software R, and the distribution that I obtained is this one. Okay, so the mean of that distribution is 50. So 50 out of 250. So basically, in not only the mean, also the mode of that distribution and the median. So basically, of these 10,000 samples we obtain, and in most of them, sorry, no, not in most of them, the value that comes more times is 50, and then values close to 50, 51, 49, 52, 48, 53, 47. Those are the most common values, and we can see that in the distribution. 50 is in the middle of the distribution, and we see that values that are less than 30 were very rare, and values more than 70 are very rare as well. So this distribution, we can actually obtain the mean, the median, the range, the minimum value, the maximum value, the standard deviation, and we can obtain percentiles. The 2.5 percentile and 97.5 percentile are very interesting. So the standard deviation of that sampling distribution is what we call the standard error. So standard error is simply the standard deviation of a sampling distribution. Now with the 2.5 percentile, which is the value in which we are going to observe 2.5% of the values on the distribution are lower than that value, and the 97.5 percentile means that that value is a value of in this axis, and the values we observed in this distribution, and only 2.5 will be higher than this value. So basically, we use the 2.5 and the 97.5 percentiles of the distribution to create an interval estimate. So if the mean of the distribution is 50, that's the point estimate, and the 2.5 and the 97.5 percentile will create what we call the 95% confidence interval, and that would be our interval estimate. Now obviously we need to transform this into proportions, because our estimation is about proportion of the population, not about yes counts in the population. Okay, this is the procedure that we use to calculate, to make an estimation of an interval. Now, there are problems with this procedure, and because of these problems, then people are using different approaches. But still, the frequentist or traditional approach is the most popular, and that's why I explain it. Now, the main problem here is that the procedure we use guarantees that 95% of the times we use the procedure, we obtain the value will be within the interval we provided. But it's about the procedure we use. So the 95% confidence, we cannot say that we are confident that the proportion of the population will be within those parameters. We cannot say anything about that. Why we cannot say anything? Because of this that we did at the beginning. We started with the assumption that the population actually has 20% of yes values and 80% of no values. So started with that assumption, then we created the confidence interval. So that assumption is based on our sample, but it may not be correct. It may not be true. So that's why we need to be very careful when we present our estimation of a parameter using the frequentist approach, that we only say what we can say. Is that given the assumption, then this is our estimation, and we cannot say that we are 95% confident that the proportion of the population is within this interval. We can only say that the procedure we use to create this interval gives a correct estimation 95% of the time.